Good evening, everybody. Today we'll discuss the stepwise approach to interpreting arterial blood gas, and we'll go fast for that, and I will concentrate on how to calculate the anion gap. For any blood gas, step 1, you should ask yourself is there is acidemia or an alkalemia. Step 2, is the primary disturbance respiratory or metabolic? Step 3, for metabolic acidosis, is there a high anion gap? Step 4, is there is any compensation and is it appropriate or not? We'll give you one example for blood gas. Step 1, we said is it acidemia or alkalemia, and all of you know that. Step 2 is the primary disturbance respiratory or metabolic. Also, I will go fast for that. One example here, you will know if the pH is 7.48, PO2 is 62, and PCO2 is 25, and bicarb is 25. Here, you will look to the pH, you'll find that the primary there is alkalemia because this is more than 7.45. If you look to the PO2 and this is arterial 62 is acceptable, you look to the PCO2, it is low because you know the normal range is 35 to 45 and bicarb is 25, which is normal. So you have here respiratory alkalosis. Okay, so here alkalosis would include pulmonary embolus or hospital acquired pneumonia, or we know the patient who is too much tachypnic, he may develop respiratory alkalosis. My main purpose of this discussion today is to discuss how to calculate the anion gap. For the metabolic acidosis, if there is a high anion gap, you will identify the type of acidosis. It will help you to narrow down the possible underlying causes. What is the anion gap? In the body, the number of cations and anions are equal. Blood tests measure most cations but only a few anions. Therefore, adding all the measured anions and the cations together leaves a gap that reflects unmeasured anion such as plasma protein albumin. Because sodium is the primary measured cation and chloride bicarb are the primary measured anions, the anion gap is calculated using the following formula: sodium minus bicarb plus chloride in between brackets. The normal anion gap is 8 to 16 millimole per liter. Some hospital adding potassium, so the formula will be sodium plus potassium minus between brackets bicarb and chloride. Here the normal range will be from 12 to 20. So the normal anion gap is 8 to 16 if you didn't add potassium, and if you add potassium the normal anion gap will be 12 to 20 millimole. Okay, here I want to mention a very important thing is about albumin. If the patient with low albumin concentration, he may have a normal anion gap. In the presence of a disorder that usually produces a high anion gap, how is this? Because the anion gap is reduced by about 2.5 millimole per liter for every 10 grams per liter for in the albumin concentration. Suppose the normal albumin is 35 and you find the albumin is 25, means here 10 gram fall, so the anion gap will be reduced by 2.5 millimole. Example, albumin is 20 and here the normal is 40, sodium is 135, potassium 3.5, chloride is 100, pH is 7.3, PCO2 is 25, bicarb is 20, lactate is 5. What is the anion gap here? And we quick review: 7.3 is acidemia, PCO2 is 25, this is low, So this is washing, means BCO is washing, and bicarb is 20. So this is partially compensated metabolic acidosis. Here you have high lactate and you have low albumin. If we calculate the anion gap, which is sodium potassium minus chloride plus bicarb, we'll see the formula like this. If we take the potassium sodium only 135 minus 100 plus 200, this will give you 15 millimole. And we said the anion gap, if we didn't add potassium, normal from 8 to 16, but here gap is 15, but albumin is 20, means from the normal it's fall 20. So you should this anion gap reduced by 5, because we said every 10 milli every 10 gram loss in fall in albumin will reduce the anion gap by 2.5. So the anion gap here is reduced by 5 millimole. So if we added this 5 over 15, the anion gap will be 20, and this is high anion gap as metabolic acidosis. Thank you, and I am very happy to receive your questions. Bye.